Microwave tubes, magnetrons, first part, series on microwave engineering, lecture number 4.31. Magnetrons are microwave tubes. They are high power, high efficiency microwave oscillators. Several types of magnetrons are there, but the variety, the category that is used at present belongs to cavity type or cylindrical type magnetron. It is also known as traveling wave type magnetron. These magnetrons are basically diodes. They have two electrodes, one cathode and one anode. In cylindrical magnetrons, cathode is in the shape of a cylindrical rod. Inside this cylindrical rod, there exist heater coils. When coils are connected to power supply, they generate heat, rising the temperature of the cathode. It leads to emission of electrons from the surface of the cathode. The cathode is surrounded by a thick block of cylindrical tubular anode. In the structure of the anode, there exist several cavities. These cavities act as resonators. Usually, the cavities are all identical, and in most of the cases, they take the shape of hole slot combination. In between cathode and anode, there exists certain cylindrical space. It is called interaction region. In this region, while the device is functioning, there exists three fields, two static fields, one rotating RF field, radial electric field, axial magnetic field. These two belong to static fields category, whereas a component of the noise, which is strengthened by the electronic bunches by transferring their energy. It is the RF rotating field. In the present session, the focus is on historical background to the development of magnetrons, types of magnetrons, and mainly on structural features of the magnetrons. Now, let us move further to the course session. Let us consider a few points as an introduction to the course session. Magnetron is a microwave oscillator. Its output falls in the microwave band. That's why it is microwave oscillator. It is oscillator. It gives out a wave with no signal input. That's why it is oscillator. It is a crossed field device. In this device, there exists electric field. It is in radial direction. There exists magnetic field. It is in axial direction. So both are perpendicular to each other. Hence, fields are at cross. That's why the device is called crossed field device. It is also called M-type tube. As already explained, focusing field, that is magnetic field, is perpendicular to accelerating electric field. Magnetic field is axial, electric field is radial. It is the first high power microwave source, helped in developing long range radars during World War II. The range of radar, it depends upon the power that it radiates. High power microwave sources, they are capable of delivering higher powers. Therefore, radar becomes capable of transmitting, radiating higher powers. Magnetron is the first high power source available to the designer of radar systems. They used this source, high power source, its high output power, to extend the range of radars. It happened during World War II. At present, it is possible to realize very high power levels of the order of several kilowatts with an higher efficiency of 80% or more. Regarding magnetrons, one point should always be kept in mind. They are capable of delivering very high power levels. They are also highly efficient systems. Getting an efficiency of 80% from a microwave tube, it is not an ordinary or it is not a simple thing. It is actually an extraordinary performance. However, they are very noisy and also they have the inability to maintain frequency or phase coherency when operated in pulsed mode. The noisy nature of the tubes, it is a serious problem, and another problem is also there with these devices, that is inability to maintain coherency in frequency as well as in phase when operated in pulsed mode is, in fact, it is a very serious shortcoming. A few points regarding historical background to the development of magnetrons. First magnetron, known as split anode magnetron. It was a simple one developed in 1920 by Albert Hull. It was consisting of two poles and it is of relatively low efficiency. The cavity version, referred to as resonant cavity magnetron. It was built by British physicist John Turton Randall with a team of British co-workers during 1937-1940. In 1940, John Randall and Harry Boot managed to increase the power output of this multi-cavity magnetron by 100 times. One point I would like to mention here is no device is developed in one day. The devices, they come to maturity after working on them for several years by several people. In 1941, the problem of frequency instability associated with this device, it was solved by strapping. We are going to discuss about this technique strapping soon. Strapping alternate cavities within the magnetron. The cavity magnetron was widely used during World War II in radar equipment. However, their use in radar itself has decreased due to the need, due to the necessity, due to the requirement of more accurate signals and development of klystrons and traveling wave tube systems for meeting these requirements. Nowadays, magnetrons are primarily used in microwave cookers. A few points regarding major types of magnetrons. Split anode magnetron. They use the static negative resistance that existed in between two anode segments for its operation. Static negative resistance. Their operation frequencies lie below the microwave region. So the signal or waveform from split anode magnetrons, it falls below microwave range. Cyclotron frequency magnetrons. They operate under the influence of synchronism between an alternating component of electric field and periodic oscillations of the electrons in a direction parallel to the field. Their frequency of operation is in microwave range. This point is okay, but their power output is low, their efficiency is also low. These are two serious drawbacks. Now, traveling wave magnetons, third type, they depend for their functioning on the interaction of electrons with a traveling EM field having a linear velocity. The discussion of us is on traveling wave magnetrons. Drawbacks. Split anode magnetrons have the disadvantage of working at frequencies which are below microwave region. Cyclotron frequency magnetrons. Their frequency is in microwave range, but their output, their efficiency, they are very low. A serious disadvantage. Please note, magnetrons in most of the applications, they remain always on. It is not like on for some time of the day and off in the remaining period. As they are always on, efficiency is an important aspect. When they are on, they are consuming power. They are taking power from the source. Out of this power, low efficiency means most of it is going waste. If this waste happens to be a small part of the day, then one may be able to accept. But as the functioning is continuous throughout the day, efficiency plays an important aspect. Low efficiency devices, they are not at all preferred in applications where the device requires to be on continuously. Now, cavity magnetrons. Cavity magnetrons, they are also called cylindrical magnetrons. These are also called as conventional magnetrons. These are high power, high efficiency microwave oscillators. They depend upon the interaction of electrons with a traveling EM wave for their operation. These are basically diodes having two electrodes with several connected re-entrant cavities. Note, cavities are resonators. They act as resonators at microwave frequency. Two types of cavities are there: non-entrant, re-entrant. If the surface wall enters into the volume of the cavity, then it is called re-entrant cavities. At microwave frequencies, cavities that are used widely belong to the category of re-entrant cavities. Here, the cavities are connected to each other through, of course, interaction space, which you are going to see soon. These are also called crossed field devices, as they employ axial DC magnetic field and radial DC voltage. If the values of these fields are adjusted properly, the electrons follow cycloid paths in the interaction space. The path of a charged particle under the influence of crossed fields is cycloid. In the interaction space of this device, crossed fields exist. Cathode emits electrons into the interaction space, interaction region, under the influence of fields, crossed fields that are existing in the interaction region. The particle traces a particular type of path. It is cycloid path. Acceleration of electrons by direct electric field and retardation by alternating field takes place simultaneously in the same interaction space. Ultimately, energy transfer takes place from DC electric field to RF via electron bunches. Here are shown two diagrams. One diagram in A, it is mainly to illustrate the structural features of cylindrical magnetrons. In B, strapping is described, illustrated. A few points regarding A. In A is cross section of the device is shown. It is actually a cylindrical magnetron like this. This is cathode. So one can see a rod inside the structure. It is cathode. Inside cathode there exist heating coils. When heating coils are connected to supply, heat gets generated. This heat raises the temperature of the cathode structure. Then the surface of the cathode releases electrons. Electrons get emitted into interaction region. Now, notice cathode is surrounded by anode block. This is anode block. In the anode block, one can see cavities. Here, the cavities are made with a hole and a slot. This is a hole, this is a slot. One can find several cavities. They are 8 in number. They need not be 8, but here it is shown. All these cavities are identical. in shape and size. Also notice these cavities are in connection with interaction space, all cavities. Therefore, interaction region or interaction space is in touch, in connection with all the cavities. Hence, one can say all these cavities are in connection with each other. From one of the cavities, output is extracted using a loop. Also notice certain parts of anode, they are named as poles, anode poles. Between two consecutive poles, there is a gap. So gap is part of anode, pole is also part of anode. Now B, diagram in B. This diagram is shown mainly to illustrate the process of strapping. First, what is strapping? It is connection of alternating poles through a ring. Here two rings are used, one inner ring, another outer ring. Two inner ring poles are connected, alternate poles. So conductive connectivity between alternate poles, they are provided by inner ring, and outer ring also provides connection between alternate poles. Here one can see two sets of alternate poles are there. Connection between one set of alternate poles is provided by inner ring, other set get interconnected by the other ring. This process of providing conductive connection between alternate poles is called strapping. Now, why strapping? The purpose of strapping is to prevent mode jumping. Magnetron, cavity magnetron, or cylindrical magnetron is capable of functioning in several modes. Each mode is associated with certain frequency. In fact, two frequencies. If mode is allowed to jump, then frequency of operation also changes, which is unwanted most of the times. In fact, it is always unwanted. Mode jumping is never preferred. To prevent mode jumping, strapping is used. Now, a few points on anode part of the device. The basic structure consists of an anode. It is a large cylindrical block of copper into which is cut holes and slots. As I already mentioned, holes and slots are a type of resonators. Other type of resonators are also possible. The holes correspond approximately to inductance and slots to capacitance, resulting in functioning of each hole slot combination as a resonant circuit. In the pi mode of operation, which is usually desired, the resonant circuit consists of parallel combination of inductance L, capacitance C, and the operation frequency of magnetron is approximately equal to that of individual resonator. Here a new term has come into being for the first time, pi mode of operation. As already mentioned, several different modes are possible when the device magnetron is functioning in one mode, one of those several modes. Alternate poles, they remain in phase, and side by side poles, they exhibit a phase difference of pi or 180 degrees. Pi radians are 180 degrees. This mode is widely employed in the design of magnetrons because it is associated with several advantages. We are going to see all those aspects in the coming sessions. So pi mode is mode in which poles, which are side by side, they have a phase difference of pi radians. Some points regarding cathode. The cathode is a solid cylindrical rod embedded with heating coils emitting electrons. It is made to withstand high temperatures caused by the back bombardment of electrons and consequent disintegration. Notice this is cathode. Cathode emits electrons. Some of the electrons, they return back to the cathode. Of course, remaining, they reach to anode and gets absorbed there. So two types of electrons exist. One type returns back to cathode. Another, they move and reach anode. We are going to see soon the electrons which return back to cathode. These are waste electrons. These are no way useful in developing the signal in the device. Only the electrons which move to anode. While moving to anode, they transfer energy to the RF field, strengthening it, developing it to large amplitude. So therefore, these electrons are only useful electrons. Now, electrons return coming back to the cathode. They bombard the cathode. So cathode must be made such that it can withstand the hit or bombardment of the electrons. It is found that relatively fat cathode can dissipate more heat than thin one. Magnetron cathodes usually belong to either barium strontium oxide type or thorium oxide type or thoriated tungsten type. To confine the electrons to interaction region, end shield disks are located at each end of the cathode. First we considered anode, then we considered cathode. Now it is the turn of interaction region. The region between anode and cathode in which electrons interact with the DC and RF fields is called interaction region. It is here the electrons emitted by the cathode interact with the DC and RF fields in such a way that electrons give up energy to the RF field. In total, there exist three fields in the interaction region of magnetron. Electric field, it is in radial direction. Magnetic field, it is in axial direction. This is magnetron, cylindrical magnetron. This is cathode. Let us say this is interaction region in between cathode and. Now in the interaction region, radial electric field, radial means like this. Axial magnetic field along the axis and rotating RF field. Electric field and magnetic field, these are static. These are DC. They come into being because sources. Radial field comes into being when a voltage source is connected between cathode and anode. Magnetic field, axial one, comes into being when a permanent magnet or electromagnet is used to establish magnetic field. And rotating RF field. What is the source of RF field? See, in the interaction region, there exists noise. Noise exists everywhere. It exists in the interaction space also. Noise can be considered as a combination of several frequency components, huge number of frequency components with amplitudes almost nil or very small amplitudes. The RF field, rotating RF field, is one from those huge number of noise components. This one particular component is picked up, selected depending upon requirements, our need, by properly choosing the dimensions, the sizes, the shapes of the cavity resonators. Some more aspects pertaining to rotating RF field we will be discussing soon. The radial electric field is produced by connecting a DC voltage source V0 across anode and cathode. Axial DC magnetic field is generated in the interaction region with the help of permanent magnets. The rotating RF field, initially very feeble, may be considered as a component of omnipresent noise. This component gets strengthened by drawing energy from the electron bunches. These are some of the points which I want to share with you for right now. To recap, in the present session, what we discussed or what we focused upon are different types of magnetrons, their historical background, structural features of cavity magnetrons. Enough for now. Hope you have enjoyed the session. See you soon again in another session. Bye bye.